Hello. Hello. Welcome to my first ever live stream. Today we will do some stuff with so today we are going to make welcome. Today we are going to basically make part 7, and thank you a lot for joining, and I'm really nervous, so please forgive me. Without further ado, let's start. So the plan for today is to basically do everything that's left with the bootloader with stage 2, and to actually start working on the kernel. So in part 8 we will start working on the kernel. The first thing we're going to do is we are going to basically create a script to automate the creation of the toolchain. And then, we'll move to GCC. We'll give up on using Watcom. It was not a very good compiler and not a big fan of it. So, I'm gonna switch to GCC. Okay, so let's get started. The first order of business is to basically create an automation script that will do all the steps required to set up the toolchain for us. I did make a recent video about that. If you haven't watched it, you might want to watch that. Let's get started with that. So first, let's just create a new folder here for build scripts. So the make file is gonna get quite big, so I would prefer to have it more modular, so I'll split it into a couple of folders, and let's create a toolchain.mk. So what we have to do here is to basically download all the scripts, to download all the source files of binutils and GCC. Then we will basically unpack them and run the configure script, run make, and then make install. Okay, so first thing first, let's start with binutils. So let's create a toolchain here, a toolchain target, which means that whenever we type make toolchain, we are going to build all the toolchain stuff, and this will depend on toolchain binutils and toolchain GCC. And we will start with chain binutils. Okay, so the first step is to download it, so let's do that. Binutils FTP. Okay, this looks like the good link. Okay, so I created a variable for this toolchain URL, for this binutils URL. Okay, and the first step is to download it, so wget using this URL. Now, if I just leave it like this, it's gonna download it inside the source, inside this project folder, but let's keep things clean, so I'm gonna create a new folder called toolchain, and we are going to download there. Okay, this would be the first step. Okay, so next, now that we have the archive downloaded, we need to unpack it. So okay, I made a little mistake here. So first I create a directory, and then I go inside and run wget. Now something about make is that each of these lines is gonna be a separate shell. It's gonna instance a separate shell for each line, so that means that whatever context we set here, like change the directory, it will not be kept for the next line. So I have to do this again. Okay, and we'll just unpack this file, and that should generate a folder called binutils-2.37. So next, let's create a build folder. Okay, then we will go into this folder and run the configure script. Okay, now for the actual arguments, what I'm going to use is, okay, I've discussed this in the previous video, but just gonna copy and paste these. Okay, so yeah, this is something that we haven't done. We haven't set the prefix directory, the prefix, which is gonna be where this is gonna get installed. So let's do that. And I'm just gonna use the same toolchain folder and i686-elf, which is our target. So if we have the 64-bit toolchain, we will have that in a separate folder. Okay, the target, yes, this is another thing we haven't set. The target is just i686-elf. Okay, then with sysroot, we already discussed this in the previous video. So with sysroot means that it's gonna get sysroot support. That's basically how you tell the build tools where your where your include files are and where your libraries are and so on. Disable NLS. We don't really want to have like other languages. We don't care about having the error messages in some other languages, so we're just going to disable that. And this is to disable the build failing if there's any warning. Okay, and next we just need to run make and make install, and that should be it. Actually, for make we can just do make and -c, I think was the argument. Yeah, -c. This is how we tell make what directory to use. And make is gonna go into this directory. Actually, we can use this make variable, which will point to the exact path where our make is. Okay, this looks good. And then make install. And of course, we want to do this in parallel because otherwise it's gonna take forever. So I'm just gonna add -j8 or something like that. Okay, so that's basically how we build binutils. Let's do the same for GCC. Okay, we are not sure what order. Actually, yeah, we know. So GCC depends on binutils. So I'm going to add that dependency here. So this means that binutils will always be built after binutils. This means that GCC will always be built after binutils. Okay, and yeah, the commands are pretty similar, so I can just copy all this. Let's do the GCC URL as well. And I'm just gonna get the latest version. Oh, whatever. It doesn't matter which one. I'll just use the XZ. It's smaller. Okay, so this time this is the GCC URL, and this time we are downloading GCC. The version is, yeah, actually it's right here. Okay, let's keep this consistent. Okay, Okay, now the configuration for make is pretty similar, but there are some minor differences. Yeah, so prefix and target are the same. So prefix is where we want to install this. Target is i686elf. Disable NLS, same as binutils. It disables the initialization, the localization of the error messages and stuff like that. Then we want to have a toolchain for C and C++, so we want to build both of these languages and without headers. This is an option so that GCC won't use the libc headers in the libgcc. We'll talk about libgcc a little bit later. But yeah, okay, so now that we have configured, the next step would be to run make. Yes, this is the new directory. And then make install, but this time we have to specify the target all-gcc and then all-target.libgcc. And then same for install. Okay, so now we should have a working script, I think. Something that I want to do here is to clean this up a little bit and to split these so that we can do some stuff in parallel. So first, let's create some variables for the versions. I don't want to type the version every time, so binutils version is 2.37, and I can just replace 2.37 everywhere else. Not here. Okay, that looks better. Same with GCC. So okay, so now what else? Yeah, so there's some repeating stuff here that I kind of want to get rid of. So let's also create some variables for that. For example, the build folder is repeating here. Okay, same with GCC. Okay, that should be a bit cleaner. Yeah, so yeah, let's also split this file up. I'm gonna create a new file, config. Okay, because we're gonna put some more stuff in here, and let's move these URLs and the version in config.mk. I'm also gonna put the target here. These at the top. Yeah, another thing about the prefix is that we want to have an absolute path, so let's get that. And yes, this is target. And then we also had the path. Now, in makefiles, whenever you use export, what that means is that this will be changed in all of these commands as well. So it's basically how you can pass environment variables to child processes, or in this case, we can also pass these variables to this make that we are calling here. So what I wanted to do here is to add prefix to the path. Actually, these are necessary. Okay. What else? Yeah, so now we want to... I'm gonna create some variables so that I can use... Okay, so target GCC, target CC, target C, and target LD, and so on, so that I can basically... I don't have to type dash target dash GCC whenever I want to write my compile commands. So what I'm going to do is just create export target CC. This is the C compiler, and this will be target dash GCC, and for C++ that's CXX, and that's G++, and the linker is LD. But actually in this case I'm just gonna use GCC for linking as well. Okay, so now we have a script that can create our toolchain, and yeah, let's see if this works. I have no idea. Okay, so I forgot to include these in the makefile. Okay, now to include something, you just call... Okay, so I want the config to be right at the beginning, so... Yeah, I'm gonna put it here. And then the toolchain stuff, let's put it a little bit lower. Yeah, I think after all it's fine, because because the first rule, this is how make works. Whenever it encounters the first rule, the first target, that's gonna be what gets executed by default, and I don't want that to be toolchain, so I'm including it after the old rule. Okay, so now if I run make toolchain, we should have a script that builds our toolchain. Yeah, now this will take a while. Yeah, if there's any issue with the sound or with anything, just let me know, okay? Yeah, I'm from Romania. Somebody is asking where I'm from. Yeah, and hello to everyone else. Yeah, thank you a lot for joining. I mean, this is very new for me. I'm really nervous, and yeah, let's see how this goes. Yeah, something I noticed here is that the warning about Git, so we should probably add this toolchain directory to git ignore. Okay. Yeah, that's great. If everything is perfect, then great. Yeah, so I think binutils is done. So fast. That was very fast. And now it's in now it's building GCC. Yeah, now as I mentioned earlier, something that I like to do here is to make this a bit more modular. So I would split this into a couple of different targets. For example, okay, so let's create a separate target for this wget. Okay, so what we're gonna do is just break this down into a couple of more targets. Toolchain binutils will depend on this file right here being downloaded, this part GZ. So let's create a dependency on that. Okay, so to build this, it depends on this file, and to get this file, we're gonna create another rule. We just need to run these two commands. Okay, so now we can do some stuff in parallel, because we can do the same thing with GCC. So let me just move this as well. So okay, this is the file name, and it's in toolchain /gcc-version.r.xz. And to get this file, what we need to do is run this wget. And yeah, if the toolchain directory already exists, we can put a -p here. So if it exists, this won't give any errors. And yeah, I can do this here as well. Okay, so I can do this from here. Yeah, and just to keep this extra clean, let's just add another phony. So basically I'm telling make to that these aren't real files. Toolchain GCC, toolchain binutils. I mean, it can figure that out by itself, but it's just the cleanest to do this. Okay, so this is gonna take a little while, so let's continue. Let's continue with the next thing on our list. Okay, I'm kind of cheating here, so let me just be honest with you. I'm kind of cheating here because I already have all this code written, and I'm just kind of looking there from time to time to see what else I did. I just did that too, so I don't forget anything. Yeah, so yeah, I think this looks pretty good. Now if we run make-j4 or something like that, it's gonna download this file while it's building binutils. So yeah, that's a save of time. That's very good. Okay, let me see if there's anything else. Oh yeah, let's also add some a clean rule. I just copied and pasted because this is really simple. I mean, this is just cleaning up the toolchain directory. So I'm just gonna delete the GCC build. So, and then also the source, which I'm just gonna replace here as well. That's something I haven't done. Yeah, so for the source directory, I don't like copying and pasting too much, so yeah, I'm gonna create toolchain dash and then the version, and that will be the source folder where this is located. And whenever we encounter this, let's just use this variable now. I think I did not do this correctly. Oh, okay, it's fine. Yeah, it also replaced this here, but it's fine. I think it's perfectly fine. And same with GCC. Okay. So now this clean command will delete everything except for the tar.xz files, and this clean toolchain all will delete everything, including the source code, the packaged source code. Okay, so this looks pretty good to me. Okay, so let's go now to this configure file that I'm trying to create here. Yeah, so previously the way I did this was in this file, and you can see here that I already have some stuff, so just gonna move this into this config file. So this way it's gonna be much easier. I don't have to search through all the make files, which might be God knows where. I just have to come here into config.make and just change a few things, and that's it. Okay, so yeah, something that I should probably do here is create some export C flags. So these will be the flags for the C compiler, which will apply to every source file. And yeah, we probably want to use C99 and also to use symbols, so -G. Okay, now something else that I have here in this make file is that I'm using actually two tool chains. One of them is basically gonna be this cross compiler that I'm building right now, and the other one will be the host, which I'm using for this tools directory here. Yeah, so for this reason, I'm just gonna create two variables here. That will be C flags, and let's also create one target C flags. And I think I'm gonna leave these the same. But, you know, if we want to add something like, I don't know, -02 to optimize stuff, then we can just go here and change this, and it's gonna be much easier than having to search through all the make files. Okay. Yeah, and I'm also gonna export everything. I want these to basically also be applied to all the modules that I have here, that because I have the makefile split into a couple of parts. Okay, I won't be using the Watcom, so I can delete these. Yeah, the C compiler is also gonna be GCC for the host. What else did I have? The linker, yes. LD equals, awesome. Gonna use just gonna use GCC for linking. I already set these in the toolchain over here. I guess I could move these. Okay, I also have this assembler, so I'm just gonna use NASM for both. Okay, so whenever we want to compile something that works on the host machine, we just run these. Whenever we want to compile something that will run on the inside the operating system, or you know, something related to the operating system, we're gonna use these variables. And yeah, this is very clean now. Yeah, another thing here is I probably want to add ASM flags. This is something that I'm gonna use later. And also the linker flags. So I'm just gonna add link flags and the libraries. And same for the host. Okay, we don't need anything right now, but we will see later if we do. Okay, so yeah, that's basically it for this configuration file here. Yeah, so let's go ahead and modify the make file now. Now I think this is kind of redundant. I don't care about the source code. I mean, I don't plan on changing this anytime soon, so I think I should just get rid of it. And yeah, same for the tools directory. Okay. The build directory, that's something that, yeah, I'm also going to move inside the config file. And I'm not going to export this because we're going to change the build directory. We're changing it right here. So for example, yeah, over here, the build directory is changed. So it's, actually it's not. Okay, so the build directory is the absolute path of the current build directory. I think I can use this for everyone. I think this would be fine to export and okay. And it looks like our cross compiler is built, so let's start using it. Okay then, yeah, so first things first. Now we want to get rid of Watcom. This is something that I've used. It has served us well until now, but it's something that I kind of want to get rid of. And that's kind of why I made these past two videos, where I basically set up the toolchain and set up the GCC cross compiler to use it. And also I made that video about protected mode, because now what we're gonna do is make stage 2 work in protected mode instead of real mode. And also we're gonna, yes, the main issue with having stage 2 in protected mode is reading the kernel and stuff like that. So it's accessing these BIOS functions after we are in protected mode. And the way we're gonna approach that is we're just gonna switch back to real mode, run the BIOS interrupt, and then go back to protected mode. I think that's gonna be the best approach, because we will also be able to use like all the memory that we need. We're not gonna have to mess with all these weird segments that I'm not a big fan of. So yeah, I think this is the best way going forward, and that's why I decided to nuke Watcom and to just use a single toolchain for everything, which would be GCC. Okay, so let's start by going to the makefile, and yeah, I also have to clean this up a little bit now, because some of these commands won't work anymore. Okay, so basically our main work is going to be here in stage 2. So let's start by creating a new stage 2. I'm going to rename this into stage 2 old. And let's create a new stage 2. And let's build it up from here. Okay, so first I'm going to move the makefile. This is something that we definitely need. And let's also move main.asm. I'm just going to rename this file to entry.asm, because this is our entry point, and I just want that to be clear. And yeah, we'll add these as we go along, but first let's start with the entry file. Okay, so yeah, we want to use GCC now. We don't want no more Watcom. And let's start with this makefile, and I'm gonna nuke all of these because we no longer need them. So we no longer need the 16-bit compiler, the 16-bit flags. Okay, the build directory is just gonna come from above, so, and actually this one as well. Okay, now for the assembly flags, we kind of want to add something to it. And we want to add this option that that NASM should output. Now, Previously we used obj files for this, but the GCC compiler or the LD linker doesn't support this format. What it does support is ELF, so we're just gonna change that to ELF. And I think I should do target ASM flags if I remember correctly. Yep. All right. Yeah, so we will collect the sources, the C sources using this wildcard. We'll also collect the assembly sources using this wildcard, and then we generate the object files here. Okay, now here, this is not gonna work anymore, so we need to change. Okay, so let's start with the compiler. For the compiler, I'm just gonna use yeah, the config. It's very handy to have this here, so I can just copy and paste. Okay, so to compile the C files, what we need to do is use the target CC compiler, and for the flags we are using these flags, so target C flags. Now the output file is -o. In GCC it's not FO, it's -o. What else do we need? Okay, so I think this looks good. Yes, -c. This way we are not gonna compile this into an executable, but we're gonna compile these into an object file. This is what flag that we need here. And I think that's it. Now for the assembler, it's basically the same. And the arguments look good. And now for linking. For linking, we will have to create a new linker script because this one's not usable. Okay, so this will be our linker script. Now, the way this is gonna work is okay, yeah, so first we want to specify the entry point, which we're gonna have as this entry label, so. And then the output format, we're still using binary. And now we have to declare all the sections. Now, previously we had a code section. Okay, so we had this entry section, and then we had the text section, which would be the code, and then we had the rest of the data. Now, LD has a lot more sections than these, and we will just add them all here to this linker script. First, I'm just going to create a variable, and this is basically going to be the physical address where our stage 2 is going to be loaded. Now, I've thought about this and I decided to change it. So previously I was loading this at address 20000 in hex, which would be, I don't know, like 100 kilobytes or something like that. But I'm just gonna change this to address 500, and the reason is because I want the segment to be 0. This is for the protected mode stuff, so we'll see later what I mean by that. Okay, so we are loading at address 500. Okay, and now we have the sections. So first we are going to tell the linker that at this current address we want to have the physical address in this phys variable. That's kind of what the statement means, is that from now on use this as the physical address. Okay, then we have the entry section. This is a section that we are going to create. Yeah, and something else that I'm doing here is I'm creating some variables. So this is basically a variable that we're gonna be able to use from either assembly or the C code, so that we know where our sections begin. And we will see why that is important a bit later. Okay, so we're telling it to create this symbol and assign to it the current address. And then we want here to emit all the stuff in the entry section, and that's what this does. Okay. Next we have the text section. What this means, basically the code. Same as before, I'm creating variables to know where each section starts, and this will contain all the stuff in the text section. Okay, let me just copy and paste this because it's easier. Next we have the data section, same as in the old stage 2. Okay, then we have a couple of extra sections that are only appear in LD. I mean, Watcom also has these, but Watcom kind of groups them together inside a single like data group. So we have the read-only data. So data would basically contain all the stuff like variables that have assigned values, and read-only data is all the constant stuff like strings, and any constants that you have declared throughout the code will be put into this read-only data section. Okay, then we have the BSS section. Now what this is, BSS is all the uninitialized data. What this means is like all the global variables that you have but aren't initialized. And normally whenever we are gonna switch into, when we call the C code, what we'll have to do is to empty this, to set all of this to 0, to basically memset all the BSS stuff to 0. Okay. And yeah, that's basically all the sections. And finally, we're gonna create another variable to mark where everything ends. Okay, this is our linker script. Really nice and clean. We have the entry section first. So yeah, this is also the order in which they will be written to the output binary file. So first is all the stuff in the entry section, then we have the code, the data, the read-only stuff, and then all the uninitialized memory. This makes a lot of sense. Okay, let's finish this makefile. Hello, hello. Yeah, so something that I will also want to do here is to add some flags okay, I'm missing the underscore here. So I'm gonna add some C flags as well, and the first one is gonna be -f freestanding. What this is gonna tell GCC is that we are trying to build something that doesn't rely on any operating system, because yeah, this is an operating system that we're building here. And then we also want to not have any standard libraries, so no stdlib. Now I know that if you watch a lot of tutorials, you'll see a lot of people use a lot of other flags. And actually I wanted to show you an article on OS Dev that you don't really need all of that. I don't remember the article title, but maybe it's this one. Or this Y. One of these two, I think it was. Yeah, and this is kind of something that a lot of people get wrong. For example, these are options that you don't need to pass to the compiler. Like, I don't know, the -m32 to tell it to compile for 32 or 64 bits. This is not necessary because we've built our cross compiler to build this specifically for our target, which in our case is i686, which is kind of the same with this one. Yeah, no std-inc. This disables the standard include directories. This is also something that's not necessary. Yeah, the reason why we don't want to use this option is because GCC actually provides some include files for us, and that's a very nice thing it does. Let me show you something. So we've built our toolchain right here, so let's go into this elf. Okay, the include folder is empty. I'm not really sure where it puts these files. Yeah, I thought they were here, but they're not. But the basic idea is that there are some headers like std-def.h, std-int.h, std-arg.h, which are also made to be freestanding. So these can be used without having to... we don't have to implement all of these ourselves. That's kind of the idea here. And that's also why we are including libgcc. That's also very important because libgcc contains a lot of stuff that's very compiler specific, very specific to how GCC works. And yeah, previously when we used Watcom, we had to implement stuff like we had to implement our own 64-bit divisions, for example. And yeah, we also had to implement those std args, so because we don't have va arg by default. But these files in GCC, these are made to work in a freestanding environment. And by not including them, we're kind of losing on that functionality, and we'd have to implement all of that stuff ourselves. And yeah, there's some stuff in there that we really don't want to implement. I mean, if you remember from the few videos back when I looked at the 64-bit division, it's a very complicated thing. It's yeah, I don't know if I can find it right now, but the idea is that if the CPU doesn't support 64 by 64-bit division, then it's extremely complicated to implement ourselves. It uses a lot of advanced mathematic concepts, and that's not something trivial. And yeah, having something like that not return correct results is a pretty nasty thing to debug. So yeah, that's why we would prefer to use libgcc if possible. Yeah, there's also no built-in, but this is also implied by freestanding. There's no reason why we need to pass it ourselves. And the stack protector, this is another thing that we kind of, maybe we want to use it. And there's some runtime stuff that we need to do in order to have this work properly, but it's actually very cool that we can use it because, for example, if we overrun some local variable in our code, then GCC can, then, you know, the GCC will generate code that can warn us about that. And yeah, that's a very cool way of finding bugs and solving them before they are actual big problem. You know, investigating a memory corruption is not easy. It's one of the nastiest things to investigate. So yeah, that's why we kind of want to use this. Okay, so I've added these C flags. I'm also gonna add the library. So target libs. We definitely want to include libgcc. So that's kind of why we built it. That's why we built it in our cross compiler. Yeah, and for link flags, we also have a couple of flags that we need to pass here. And that will be our linker script, which is linker.ld, and then also no stdlib. Okay. Now we are gonna replace this older, the Watcom linker. We're gonna replace this with this target LD that we created here. Then we will pass these linker flags. The output file will be stage2.bin, same as before. Now for the object files, here we can just use the syntax here instead of. So this means the target, which would be this part, and this would include the rest. Actually, this one is just the first one. To include all of them, we need to use this symbol, whatever this is. Okay, and this map file is also something that we can create with LD, and the way we specify that is with -WL, comma, and then -map equals, and then the path to the map file, which would be, I will use the same path. Okay, and we can delete this now. Okay, I think this looks good. Yep, this looks good to me. Yeah, so let's go into the entry now. And we are going to change this from this stuff, which was Watcom specific, to section.entry. And that's it. Okay, I haven't added the C file yet. I'm just gonna comment this and make sure that I can build. Okay, let's see if this works, if I got anything wrong. No, I did not. Okay. Okay, so the next step is to basically implement switching to protected mode. So let's do that right here. Okay, we'll take care of the C stuff later, but first let's take care of switching to protected mode. Alright, so if you remember the video I did previously on this, actually let's just copy the code from there. There's no point in rewriting it if we don't have to. Yeah, I can create a new file, but I mean, this is something that I only have to do like once, and that's why I won't. Yeah, so in the protected mode video, I made the switch. You can go ahead and watch that video. I explained how all of this stuff works. But I can go over it again. Yeah, so the basic steps are really simple. We just need to enable the 820 gate. Yeah, of course, disable the interrupts first, because those won't work till we set our own interrupt vector table. But yeah, enable the 820 gate. That's kind of like a hack which was done on older computers, because the 8086 processor had the 20th bit, it was kind of set to 0 so that it could emulate. Okay, let me go over this again. So a long time ago, on the 8086 processor had basically 20 address lines, and whenever you reached the end, if you type, for example, the address FFFF, okay, so this would be equivalent to something above 1 megabyte. This is something like, if I remember correctly, 100 FFF or something like that. It's basically this multiplied by 16 plus this. So it's FFFF 0 plus FFFF. And that will give a number above 1 megabyte. And whenever you did that on this 8086 processor, it basically looped around to the beginning. Now, some programs relied on this behavior, and in order to prevent that from being an issue, on the 286 machines that were launched later, they basically created this 820 gate. So the 20th bit was set to 0, and you had to manually enable it if you wanted to use more than 1 megabyte of memory. And then we load the global descriptor table. That's the third step. And yeah, let's add that as well here. Yeah, actually I'm just gonna copy everything, because this works very well, and there's no reason to go and implement this again. Okay, yeah, and we can stop here at this print. We don't need to go back into real mode, so I can delete the rest of this stuff. Okay, and to hold, I mean, there are two methods to hold. You can disable interrupts and then call hold, or you can just loop, make an infinite loop, basically. Alright, so that would be the switch to protected mode. Yeah, and we also set the global descriptor table. This is basically related to the segmentation feature of the 286 and all the processors that were launched after that. Yeah, so basically here what I did is I set up 4 segments. First two are 32-bit data segments which do a flat mapping, which means that we can basically use whatever address we want. We don't have to deal with segmentation at all. And for the 16-bit code segments, these are necessary to make the switch back to real mode. And yeah, as I mentioned previously, that's something that we will have to do later. Okay, what else is there to do here? Yeah, so we kind of have to do the thing that I mentioned to zero out the BSS section. Yeah, so I mentioned that this is the uninitialized variables, and that's something that we have to manually do before giving control to the C code. Yeah, so right here, that's something that will probably be lost, so we should save this to a temporary variable somewhere. We don't no longer need these, and let's also create a variable for the boot drive. Okay. Yeah, there's no reason to enable interrupts here. You can just leave them off. And this is redundant. Okay, so now we have saved this boot drive. And whenever we want to pass control to the C code, all we have to do is just push it to the stack. Okay, so this, also this is 32 bits, so we need to make, did I mess this up? Yeah, so here, okay, this is correct, but here we need to set up to basically, I'm just gonna empty the entire EDX register. I'm just gonna set it to 0, then put the boot drive there, and then push it to the stack. And then call the C code that I'm gonna include in a few minutes. Okay. Yeah, and yeah, I mentioned clearing off BSS, so let's do that as well. To do that, what I'm gonna do is use these symbols that I created here. So BSS start and end, we'll delimit where these are. So first BSS start, we can just so these are basically just symbols that are created. We can declare them. Okay, let's declare them at the beginning here somewhere as external, and also the end. Okay, now to zero out BSS. Okay, so first let's put into a register like EDI the address of BSS start. Then we want to put the length in CX, in ECX this time. And now we need to subtract this BSS start, so sub ECX EDI. So we are subtracting to get the size, because this is going to give us the end position. So we want to get the size. And then what we can do is set AL to 0 and then use store string byte. And repeat that. And yeah, so store string byte, what it does is it takes whatever value we have in AL and it stores it into the memory pointed by EDI, and then it will increment EDI. And rep, it basically gonna repeat all of this until CX reaches 0. So it's gonna count until whatever value we have in ECX, which is very cool. And yeah, we should also clear the direction flag, because if this flag is set, then it's gonna go backwards instead of forwards. We don't want to do that. Okay, so that's basically it. All we have here is to call the C code, and let's add a main file now. Okay, we can't do this yet, but I just want to add this C start here. Yeah, and there's also changes already. So stdint, I mentioned that this is now a standard file that we don't no longer need to implement. We can delete it from here as well. We had min and max here. Okay, I'll delete them in just a moment. Let's see if this compiles. And what else? Yeah, so I kind of want to use the cdecl calling convention to... That's not how I do it in... Okay, in GCC I do it by using attribute and then cdecl. And I think that's everything that I need to do. Okay, let's see if this works. Okay, I should comment these as well. Okay, so now we have a tiny little thing which basically switches to protected mode and then doesn't do anything. Yeah, so let's make it do something more interesting. Let's start adding more of these files into stage 2. And I will start with stdio because we want to have printf. We definitely want to have printf, so let's start with these. Okay, now I mentioned that in... yes, first things first, we are now in protected mode, so we can no longer use the BIOS to print characters. We have to do it in the protected mode way, which is by writing directly into memory at address B8000. Yeah, so let's change that. First, let's declare. Yeah, I'm probably not gonna need this anymore. And stdint is a standard library file, so I can just use this syntax. Yeah, also I no longer need to have these far pointers. That is no longer the case in... and also I no longer need to have cdecal here, because now I can do include std_arg.h, which is gonna be really cool because we no longer have to do this manually. Okay, yeah, so uint 8t. Yes, so that's the address where the screen buffer is, the VGA buffer, and all we need to do to print a character is just write to this buffer. We'll also need a position, so let's create screen X initialized to 0 and screen Y initialized to 0. And in order to print a character, what we need to do is calculate the position, which is... oh yeah, and we will also need screen width, and the standard is 80 by 25. And the screen height is 25. Okay, so all I have to do here is to just set gscreenBuffer of screen Y multiplied by the width plus screen X and everything multiplied by 2. Screen Y multiplied by the height, the width, sorry, plus the X position. Okay. Yes, this looks good. Actually, let's create another function to do this. Void put chr into the position int X, int Y, and the character. This will be cleaner. X, Y, okay. So here I can just call this function of screen X, screen Y, and character C. Okay, let's also create a function to put color. And all I need to do that is just add one here. So yeah, let me see. Okay, so yeah, what do we need to do in order to write a character? Just call this, and now we need to increment the screen position. So screen x plus plus, but here's something that might happen. What if this character is a new line? Then we need to handle it in a different way, because if we just do this, we're gonna get something weird. Yes, hello. Yes, I'm reading the chat. Okay, and also if this is more than screen width, then we need to go to the next line. So okay, let's handle first the special characters. Switch C. So if we get a new line, what we need to do is to basically increment the set screen x to 0 and increment screen y. There's also the \r, which would be the carriage return, I think. And in this case, all we have to do is just this first instruction, which to set the screen position to 0. We also have tabs. That's another special character. And for tabs, the normal behavior of a tab character is to basically move forward to position. Okay, so what we're gonna do is we're gonna do a for loop up to 4 minus the screen x. The remainder of this divided by 4. And the basic logic here is we're kind of calculating how many characters are left until we reach a tab stop. And the tab stops, I chose them to be 4 characters. You can use 8 or whatever you want here. But okay, so the number of characters left until the next tab stop are basically the current position, the remainder of the current position divided by 4. That's gonna give us the current. So basically how many characters we are past the previous tab point, and we need to subtract that from 4 to get how many characters are left to the next tab point. And we can just call footc of a space character. So we just want to print some spaces there. And the reason why we're doing this instead of just increasing this is because, for example, if we use the carriage return to return to the beginning of the line, whenever we type a space or we type a tab, we kind of want to replace what was there before. So that's the idea here. Okay. Yeah, and if none of these special cases, then we just do the normal print. And we increment the x position of the screen coordinate. Okay, now if screen x is smaller or equal to the screen width, we need to move to the next line. Okay, yeah, I think this looks good. All right, we'll see in just a moment. Now putThis looks good. We just need to call putC for every character. This is no longer necessary. We no longer need R pointers. Okay, for Boolean, there's an std bool header for booleans in C. Then for the periodic arguments, Yeah, we no longer need cdecal, and for the variadic arguments, we no longer need to do this weird stuff that we did here. We just use va list. And then we call a start of the list args, and then we give the last known argument, which in our case is fmt format. Okay, this is no longer necessary. Okay, now whenever we need to use this, okay, so now let's see when we use the old argp. Now we need to change that to how to use the va list instead. So for that, yeah, the first occurrence is right here. Yeah, to get this, what we need to do is just get va arg of args, and the type in our case is int, because since we are in 32-bit protected mode, all the types are going all the types that are pushed to the stack, so all the values that are pushed to the stack are going to be cast into the nearest 32-bit value. In this case, int. Okay, yeah, I think this is correct, and we no longer need this argp++. Yes, I think this error is coming from VS Code, because I don't think there's a compiler error here. 39. Okay, yeah. So this is coming from VS Code, not from the compiler. Okay. For strings, we no longer have long strings. We no longer have bar pointers, since so we no longer care about that case. And all we have to do here is to just take whatever argument we get here and cast it to a const char pointer. And this is also no longer necessary. So this is going to be a pointer. Pointers are automatically 32 bits, so this should be fine. Okay, this looks good. Yes, and next we have this printf number. Now this is something that will require a bit more effort, and the way I thought about this is to basically split this printf number into two. One will be a print to print a signed number, and the other to print an unsigned number. Okay, and a lot of this stuff will no longer be necessary that I did here. I mean, a lot of this stuff, like taking whatever value it is and casting it to unsigned int or unsigned long, this is no longer gonna be necessary. Okay, so I'm just gonna take this and just gonna move this above this printf. And let's have unsigned first. And we're just gonna get the number as an unsigned long. We no longer need the length and also the sign. We just need the radix. Okay, now in order to do this, these two are also no longer necessary. Okay, all of this process length stuff, I can just delete this because it's no longer necessary. And yeah, how do we convert a number to string? We just divide it by 10 and take the remainders and then reverse the order. yeah, we no longer need to do this since we are using libgcc, so we can just okay, and then we also want to divide number by radix and then set the next character to the hex chars of the remainder. Yes, I think this looks good. We don't care about the sign right here. And then, yes, printing the number in reversed order, and we no longer need to return anything as well. Okay, I also have to move this X chars to be above this printf unsigned. And okay, now let's create the signed version of this, which is gonna be much simpler. Okay, so in the signed case, we will just compare number to 0. So if number is smaller than 0, we just need to print a minus. And then we just call printf unsigned of minus number. And if the number is greater than 0, we just call printf unsigned of that number. And yes, the radix. Okay, let me just move this so we don't have to forward declare these functions, and I think this looks good. Okay, so now let's go here and fix this. I'm gonna create a variable here to specify if okay, let's let me see how to do this. Okay, so I is a okay, so we have the length, we also have these short or long specifiers, so we have the length and we also have this these specifiers. Okay, so how I'm gonna do it is let's create a variable here to tell if this is a number or not. Okay, this looks good. And basically, whenever we encounter this, we will also say number equals true. So I can remove this from here. And this as well. Okay, and now we need to handle if this is a number. And we're gonna have two cases, if the number is signed or unsigned. So if signed, then we will have to call that printf signed, otherwise the other one. Yes, hello to all the new guys. Yeah, and we also need to think about the length. So if the length, okay, so for all the short lengths, meaning that short, 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 and normal, so and default. So all of these will have a single case. Default actually. And for these we're gonna call printf. Okay, so this is signed, so printf signed, and our va arg of args, and we're just gonna cast, because all of these will basically be cast to an int, so it doesn't matter if it's a short, if it's a like an 8-bit or 16-bit, it doesn't matter because they're all gonna be cast to ints. And then we need to specify the base, which is radix. Okay, and same for the long length. Yeah, that's a good question. So long is, yeah, we're just gonna handle long separately, because this kind of depends on the compilers. For the long type, some compilers will need to have the long be 32-bit, no matter if you are in 32 or 64-bit, and for some compilers long is 64-bit, so that kind of depends on the compiler. That's compiler dependent, so just gonna handle it separately here. And if it's long, then okay, and we don't care about the default because we shouldn't have any. Okay, this looks pretty good. Okay, so for the unsigned case, all I have to do is just copy and paste this, and else. That means that it's unsigned, so I'm just gonna use the unsigned functions. And unsigned int, unsigned long, and unsigned long. Alright, I think that should cover all the cases that we have. Then we reset as we did previously. Yeah, the rest looks good. And let's see, what errors do we have here? Okay, let's get rid of this. Yeah, so previously I had this Watcom configuration. Let's just change this to GCC. These are no longer relevant. The compiler path is basically in the workspace folder, toolchain i686-elf/bin/i686-elf-gcc. And let's use the IntelliSense mode of GCC. And the compiler args, we're using std equals c99, freestanding, and no stdlib. Yeah, and I hope Okay, let's see if we got rid of the errors. I'm still getting these errors. I wonder if... Okay, I still have some issue. Ah, okay, so this function, because far no longer exists. Yeah, so this is a function that I had to basically dump some memory. And yeah, now printing this, the carriage return is no longer necessary. No, wherever I had that before. Alright, so this looks almost good, except that we're getting now errors with related to this. Yeah, so these are exactly what I was talking about. These are the problems. This is what happens if you don't include libgcc. You get errors related to these functions, and these are exactly the 64-bit divisions I was talking about. But the problem I have here is very simple. I just forgot to add these libraries to the linker command. Okay, now it should work. Yay, it works. And let's see if we can print some text from the hello from stage 2. Yes, I forgot to include stdio.h. What else did I forget? Oh yeah, it's printf. Yeah, let's see if I have any junk here. Oh yes, this is something that I don't need. And yeah, for printing buffers, I previously had a 16-bit bootloader, but now we are in 32-bit. Let's just use an unsigned here, uint 32. Okay, what else? Yes, now we can try this. I think I know what I forgot. So inside the entry, I commented this function call of cstart. And something else about GCC is that it doesn't add the underscore at the beginning. So I think this should be good. Let's just get rid of... Okay, let's just have extern start and... Okay. This is annoying. And then run. Something doesn't seem to be working properly, and I have no idea what it could be. Let me just check. Yeah, so we are basically making the switch to protected mode. I mean, this should be fine. Oh yeah, you're right. Thank you. Thank you, Onyxer, for the suggestion. But that's not the problem. Let me see what else it could be. This looks good. Okay, so yeah, I'm just using Kubuntu. That's my Linux distro. of choice. Yeah, let's debug. So I'm just gonna use box. Maybe you've seen this tool, but basically the way this works is you run it with, you basically create this box config file where you set all of these options, and yeah, then I'm just gonna using -f box config to call this file. Yeah, so how can we debug this? So yeah, let me check if in stage 1 I'm putting it in the right place. Okay, so it should be, oh, that's the issue, because it should be offset 500 in hex, not in decimal, and I think that was my problem. Looks like there's something else as well. Okay, so let's run this debugger and see what exactly is happening. So I'm just gonna stop at address 500. So to get that window, you just go to View and disassemble, or you press Ctrl D. And now I'm gonna double click here. So now I'm putting a breakpoint. And yes, we are reaching the stage 2. And I ran this disassemble again because so I can see my code. Okay, and let's also look at the assembly entry.sm. Something else I should check is to see if this is built correctly. Yep. So looking in stage2.map, I can see that the entry point is set at address 500, and also the entry label from that entry.asm file is also at address 500, which is very good. If this was at the wrong address, then I would have had an issue with this. Yeah, I'll add the cursor position in after fixing this problem I'm having here. Okay, let's see what else. Yeah, I shouldn't have killed this. Okay, so now let's just go step by step and see what exactly is happening and why it's not working. I have my reference. I know why. I know what's not why. No, actually, it's fine. I thought that this would be the issue, but it's not. Yeah, let's go step by step. Okay, so first I disable the interrupts, and then I save the boot drive. Okay, then I enable the 820 gate. I can just jump over that, and I think that is good. Then I load the GDT. I'm just gonna jump over that as well. And then I will set the protection enable flag. And here we jump into protected mode, and yeah, we are in protected mode. So this part worked correctly. The last 2 lines in entry.asm, what are those? Yes, you're right. That shouldn't be here. I don't know. I have no idea how it got there. Yeah, actually, when I copied and pasted, you're right. Does that fix it? No, it doesn't. The music stopped. Oh no. Okay, yeah, let's see. Let's do this again. Okay, so I can jump over this all the way to 32 bits. So right here. And continue. Okay. And now I should be at this statement here. So I'm setting up the segment registers. Okay, now here, just making sure that nothing is wrong. And yeah, that looks right. At address FFC is where the uninitialized section begins, and at 1004 is where it ends, and the difference should be 8. Yeah, I think that's okay. Okay, and then I'm cleaning up EDX, setting the boot drive in DL, and then calling start. And now what? And now we should be in the start method. Okay, so it looks like the issue is actually with either with printf or... So it's not a... Okay, so this is basically the code generated by the compiler, the entering the stack frame. And here, I think... Okay. Yeah, so here it's setting up the call to this printf function, and now we are calling printf. Now this gets a bit more complicated. It means that something is wrong in printf. Not sure what, but let's take a look. Yeah, now obviously this is a bit more complicated. Yeah, so here's where we are setting these variables. Okay, then we have this jump, which I think is going into the... it's the while loop. Yeah, so this is basically testing the exit condition of the while loop. And now we are at this switch. Okay, and it's entering one of these. Yes, I know what I did wrong. I did not call the end args. That's one thing I didn't do. Not sure if this is the only problem, but I'm not sure if this would cause the problem with let me see. Yeah, so at this point I'm just comparing with the reference that I have, seeing if I missed anything here. The address is B8000, that is correct. Not really sure what I did wrong. Yeah. Yeah, it's not that. Okay, so let's just follow the logic a bit and see if we can spot the error. So we are initializing this VA list using the format. And while we still have characters in the format string, we are checking the current state. If we are in the normal state, all we have to do is just call putc of the with the current character. And putc seems to work okay, I think. Yeah, this is the problem. So I forgot to set this equals to the character. Yeah, I don't know what I was doing here. That's not the only issue. That's weird. I'm just gonna run make clean. I mean, who knows what files I have here in the build directory that are left from a long time ago. Okay, I'm still not seeing anything. So let's think. Okay, something I kind of want to check here is that I'm not, oh, I am triple faulting. Okay, so it looks like I'm encountering a triple fault here. You can see that if I just click continue over and over, it's gonna restart. So that means that I really messed something up. No idea what, but maybe. I wonder why that could be. Call start. I wonder if maybe this is the problem. Let me just make sure if it's not this. Nope. Yeah, there's no point, no reason why this would fail. Just to be sure, let's just add an infinite loop here to make sure we're not getting out of the C code. Okay, I don't think we are we still rebooting? Yes, we are still rebooting. I have no idea what I did wrong. I think I know what I did wrong. I think this stack is not good. Okay. DS. Yeah, so I'm using the stack that was set up by the stage 1. But actually it's okay, it's fine. So DS would be 0 since we have this loaded at segment 0, and I think we are setting the stack. Yes, we are setting the stack here, so this should be set to 0. This shouldn't be an issue. And we are setting the stack pointer to 0. What this means is that whenever we push the first thing to the stack, it's gonna wrap around to wait a second. Because in 32 bits, yeah, because we are jumping to 32 bits, and the 32-bit, is this correct? Yeah, the stack is fine. And the stack registers are not fine. Okay, yeah, let's set this to FFFF0, because I think what's happening is that we are wrapping around. So whenever we are in 32 bits, SP is again 0, because I mean, this will clean up the stack, this will clean up the stack, so now SP will be 0. And when we reach this push here, what's gonna happen is that the stack will wrap around, but this time it's not gonna wrap around to FFFF, it's gonna wrap around to the 32-bit maximum value. And that's not valid memory, so I think that's probably what my problem is here. Yes, that was the problem. You can see here, hello from stage 2. Yay! Found the problem. All right, so now let's implement a couple of extra stuff. As someone mentioned in the chat, we will implement the set cursor position. And we will also implement the clear screen. So let's start with the clear screen because that one is easier. Why did the music stop again? What do you think? Should I leave the music or without the music? Do you prefer with or without? What do you think? Yeah, always when I code, I listen to a lot of music, so I never like coding in silence. Yeah, so for the clear screen, all we have to do for clear screen is to basically go into all the pixels, into all the characters actually, and just set them to default or to 0. Yeah, so start with the Y. And here all we do is just call put character at XY, just put the null character. And for the color, let's have a default color there. And 7 is like the usual default color, which is light gray text with a black background. Of course, we can change this, but I'm not going to. And yeah, I think that's it. Yeah, let's also declare this clear screen function in stdio.h. Yay, and now we have a clear screen. Okay, there are a couple of extra things we need to do for the terminal. One of them is setting the cursor, of course, and then scrolling. Because right now, if we fill the screen, we're just gonna write past the screen, which is not good. Okay. So for setting the cursor, yes, for setting the cursor, we will need a to implement. Yeah, we will need to basically write to a specific port. In order to do that, we have to use assembly. So let's create assembly wrapper for that. So I'm just going to create this x86.asm, and I'm going to implement the output B and import B. Okay. This is 32 bits, and to basically write that to, we need to get the value from the stack, which would be, okay, so there are two things that we need to get. We need to get the port and the value we want to write from the stack, and that would be at ESP plus 4, because the first thing that we have on the stack is the return address, and then there's the first argument, which is in this case the port, and the second argument is at ESP plus 8, because everything on the stack is 4 bytes at least. And then we call the out port out dxal. Now the reason why I'm using dx here is because that's actually a restriction of the out port instruction. So you can see that you can either use with an immediate value, what this means is a constant, or you can output with dx. That's basically how this instruction is wired in the processor. And let's return. I haven't set here like the proper way of writing a function, and the reason why is because it's really simple. We don't need to use the stack at all, so that's kind of why I didn't set up the stack frame here. And it doesn't really matter that much. And let's also do the same for the import instruction. Now the way this works is we basically have just the port, but we don't need this, and we call in, and I think the order of the registers, I should change it. Yep. And I'm reading 1 byte in from the port dx, and then I'm returning it. I don't have to do anything here. Actually, I should clear EAX. Okay. So that's basically it for reading and writing from ports. Now let's define this in a header file. Okay, and out port is just writing to a 16-bit port, an 8-bit value. And for the import, we just return a byte. Yep, and that's basically it. Yeah, is there anything else? I don't think there's anything else we need to do here. I think that's just gonna work. And Now here we have to, in order to set the cursor, we basically need to write to a VGA port telling it to move the cursor. And to do that, the port is, let me just check. Yes, so first we need to calculate the position, which will be y divided by the screen width plus x. And then we write, okay, so let's include x86.h. And yeah, in order to do this, we basically need to write two commands. The first one is on port 3D4. The command is F. Now what this means is, let's actually see what this means. Okay, yeah, so 3D4. What is this port? Okay, so we're basically setting value F. What does that mean? I don't see it here. Anyway, I mean, if you look it up online, that's basically how you have to, how you set the cursor. I can't find any information about what the commands are, and yeah, so basically what you're doing here, we are writing to a register using this command, and we're telling it what register, and then for the second command we are telling it what value to set to that register, but I can't find the 0xf. Yeah, but it's not this. This is the wrong. Yeah, I don't know. But I'm pretty sure that you can find this information somewhere. Yeah, and what we write here is 3D4, and the value we are setting is basically the first byte. So basically the lower byte we are setting on this port, and the upper byte we are setting on the next port, which is 3D5. And the command is E. Okay, and we are setting the upper byte, so let's shift this to the right by 8 bits, and then we can do this mask. Yep. And now we just need to call this from C whenever the screen position, whenever the cursor changes. So basically here, actually I think I can just do it once at the end. Okay, let's see. Yeah, and also in clear screen. Oh yeah, that's another thing I forgot here. In clear screen, I should set these to 0. Okay, and I think we are good. Yeah, next, let's see if this works. And next we have the scrolling. Oh, come on. What else did I mess up this time? Yes, I know what I messed up this time. So I haven't... no, it's actually correct. I thought that I forgot to use cdecal here, but it looks good. Let me... Does this look good? This is odd. Are the ports correct? Hello. Again. I don't know what seems to be the problem. So this problem started happening after... What? Okay, so... I mean, this should be fine. Okay, let's run the debugger and see what's going on. Okay, we're not triple faulting, but we are... That's odd. That's very odd. What is happening? Alright, debugger it is. So let's go to address. Yeah, actually, I think the problem is happening somewhere, either when we call this output. I'm not really sure when it's happening. Let's see if this works correctly. So let's go into stage2.map and see. So output is in at address 5C0. So to debug it, I just need to type 5C0. What is this? Yeah, okay, this looks good. So I'm just gonna continue and press reset here. Okay, so we should be writing to port 3D4. This looks good. The value in L is 15. Why is it 15? Because this should be the clear screen. Okay. And then we are returning normally. I'm not really sure. Was it that for loop? I don't think this should be necessary, but let's just make sure. Am I messing up the stack maybe? And so let's see. 5C0. Maybe I'm messing up the stack. Let's see if what we're getting the second time. So first time it's set to F, which is kind of odd, but it shouldn't be F. That doesn't look right. Because we're calling clear screen first, and in clear screen we are setting it to 0. Actually, no. Yeah, it's good. It's good. Because put CHR and put color don't modify the cursor. So yeah, the first time it should be 0, 0. So why is it 15? Something's not right with the stack. But what? Yeah, something I don't know, I have a strange issue with box and I cannot inspect the memory. I have no idea why. Because if I go and want to see, for example, the stack, it just freezes and I can't use it anymore. Yeah, box isn't the best tool out there. Yeah, great. What could it be? I think this set cursor is the... Okay, so if I don't call set cursor... I mean, this looks fine. Doesn't seem to be any problem here. So the problem appeared after doing this first output call. Yeah, and I still wonder if I'm... messing up the stack. Yeah, so let's put a breakpoint at 5... What was it? 5C0. Okay, so still getting this F, which is, I find, odd. No, I don't think it's the number of sectors. That's not... No. The stage 1 works fine. It loads fine. It's not that. I think there might be some issue here where I'm messing up the stack. Okay, so the second time I get this called, dx is also 3d4, which is also correct. This would be the second statement here. And oh yeah, I forgot. So that F was actually this here. I thought there was a problem, but there isn't. Okay, and we are writing that, and that looks good. And then we should do the second. C0. Okay, so the first time I'm writing F, that is correct, to port 3D4, and that is also correct. And the second time I am writing the position 0 to byte to also port 3D4, which is also correct. And the second time I'm writing to port 3D5, so E to port 3D5, and then I'm writing 0 to port 3D5, and this looks correct. So I don't understand what the problem is here. Okay, let's go step by step and see what happens. Okay, so this is the leave from the clear screen function. Okay, and now we should be in the start function in main. And we are pushing the address of the... Okay, this looks fine. Okay, let's see the next time we get here what we get. So the next time we're setting the cursor, it is F and 3D4. This looks correct. Then, yeah, set position 1. That also looks good. Then, okay, this looks good. This looks good. And for some reason the cursor is still here. But anyway. So then we have 15 at address 3D4. That also looks good. Don't see anything wrong. We're not writing to any invalid registers. Okay, here's where it goes wrong. What the hell is happening? There's something that I forgot. Okay. Okay, so that looks good. Yeah, this should look good. I mean, I don't see any problems. Oh, I saw the problem. Yeah, this was it. So I was setting... Okay, so the rule here is that we need to set the register that we want to write to in 3D4, and then to actually write the value to 3D5. That was the issue here. So that's fixed now, and we should have the cursor move now. Yay! Cursor is working now. Okay, let's just let's do the scroll back next. Okay, so basically whenever we get to whenever we get to the screen height, we basically want to scroll everything to move all the text up, and then we have another line that we can use. Okay, so to implement that, let's start by writing a scrollback function. And let's get the number of lines as a parameter. And for the implementation, we basically have to iterate from... Okay, so we have to move all the stuff up. For that, let's create two new functions. This time it's get character and get color. So we don't have to mess with these again. And we just need to return this value here. Okay, and now in scroll back, so we basically need to iterate from where? From lines and then all the way to the end. Okay, and for the X, we don't really... X is from 0 to screen width. Okay, and all we have to do here is just call put char of y minus lines. Of x and y minus lines, yes. And the character is get char of x and y. And same for the color. All right, and now we need to clear out all the last lines. So let's clear those. Height minus lines. Y is smaller than screen height. And same for the X, and I'm just gonna use this to clear them. Okay, so that's basically the implementation of scrollback. And whenever we get the... Okay, let's also do this here. So we are gonna actually decrement the screen Y by the number of lines that we scrolled by. Okay, and yes, now we need to just call this whenever we reach the screen height. So if screen Y is greater or equal to the screen height, we're just gonna scroll back by one line. Okay, now let's test this. So there are 25 lines, so let's just write up to 30. And this way we are also testing that our format works. Okay, so I forgot to add a new line. But yeah, we are scrolling. Yay! We have scroll back. Yes, so that is great. Now, what do you think, guys? Did you enjoy this? Did you... Because, yeah, it's been like almost 2.5 hours, and let me think about this. So what we have to do next is to basically port the rest of the files that we haven't ported. We need to add the disk functions and then the fat driver. And I'm kind of... Okay, so let's do the disk right now, because that's gonna be a bit more complicated. You know, that's kind of... Yeah, I'm glad that you're enjoying this. Yeah, if there are any questions, feel free to ask me, because I'm kind of coding here, and I'm trying to explain as I go, but I don't know if you understand everything, so just please let me know if there's anything. Yeah, the kernel, yeah, that's right. That's gonna be after implementing the fat stuff, so we have to basically put everything here, and then we do the kernel, and I don't think we're gonna have enough time today, and I'm thinking of doing it like a part 2. So what I'm gonna do right now is okay, so I can stay for maybe another half hour, maybe a little more, and then we'll call it. I'm gonna implement the disk reading functions, and then we'll do the fat and the rest in a part 2. Does that sound good? Because this took way longer than I expected, obviously. And yeah, with all the problems, with all the debugging, it took a while. Yeah, let's do the disk now, and then we'll call it and do the rest in part 2. Okay, so for the disk, now this is where I said that we are gonna switch back to real mode, do the disk operation, and then switch back to protected mode. So I kind of did that in the video about protected mode. It was towards the end, and I'm just gonna show you what I did there. I'm not gonna go ahead and implement that again. I mean, it's not that long, it's not that complicated, but let me just show you. Alright, so in this file over here, towards the end, I went back to protected mode, to real mode. And what I did here was, so first you just need to jump into a 16-bit segment. That's kind of why I set up the GDT to have these 16-bit segments here. So that's basically all you have to do to jump into 16-bit protected mode. But to get into 16-bit real mode, there's a few more steps. And the steps are, let me just go back. Okay, so after you jump back into 16-bit protected mode, then you disable the protected mode bit from the control register 0. That's kind of what I did here. And then all you have to do is just jump to real mode. Just jump to real mode, basically. This is now a real mode segment, and this is a real mode address. Now, this is kind of, I was saying earlier that I am, so I'm loading this, yeah, kernel load segment. That's not the kernel, that's just stage 2. But you get the point. Yeah, that looks better, right? I don't want to mislead anyone. So basically here I am loading the at segment 0, because it's a lot easier to set this up. Because otherwise, whenever I have, so if I go into entry.asm, now here, for example, I'm using this gboot drive label. And this is actually something that's linked, I mean, this is a dynamic symbol. This is a symbol that the linker solves, basically. So in the linker, we told it that we are starting from address 500. Now, if I were to change this to a higher value, like, I don't know, 10,000 or something like that, I think we will get a linker error. Relocation truncated to fit whatever against entry. And this is kind of the problem that I've been encountering with this, is that all the labels that are here in real mode, they are 16-bit offsets, but the value that I gave here to the linker, it doesn't fit in 16 bits. This needs more than 16 bits. 16 bits would be just the last four digits. But yeah, that's kind of the issue here, and that's why I wanted to use segment 0, because otherwise we encounter this problem, and yeah, we can't link properly the 16-bit code with the rest of the 32-bit code. Yeah, so let me just change this back. All right. Yeah, so let's go into x86.asm, and what I'm going to do here is write a macro. I'm actually going to write two macros. One to jump into protected mode and one to jump into real mode. So let's start with the real mode, because that's the logical next step. Okay. So we are creating a macro, which is called x86 and enter real mode, and doesn't have any arguments. That's what the 0 means. This is the syntax used by NASM. Yeah, and in here what we are gonna do is basically we are starting in 32 bits, so make sure to specify that, and then just like I did here, I need to do this particular jump. Okay, now the thing is here that I have to declare these labels, and that's kind of another reason why I cannot create a function to do this, because the stack would be messed up and a lot of things would be weird. The stack, so whenever you push something to the stack, it would basically okay, so if I created a function called enter real mode, whenever you call it, the CPU would basically push a 32-bit return address to the stack, and whenever we want to return from that function, if we are in 16-bit real mode, then we kind of have to modify the stack so that we can return properly, and we have to make a conversion from and you know, that's kind of just makes things more complicated. So let's keep things simpler and use a macro. Now in NASM, if you use this period in front of something, then this label is going to be local. So for example, if I add a label like, I don't know, test here, now this label is local to basically this previous label. I can also create another test here, and this is gonna work. So if I call jump test, the assembler will know that this is local to basically this label here. And you can also call these using absolute. So for example, if I want to jump here, I can just call jump and then the big label dot this nested label. So this is how I would access these if I'm outside the scope, basically. All right. So this is why these labels are gonna work. This is why this works. Okay, so now we are in 16-bit protected mode, so we want to switch to 16 bits. And then we have, yes, we are gonna disable the protected mode bit and jump to real mode. So I'm just gonna copy all of this stuff up until the enable interrupts. Okay, and I think this looks good. Okay, and I am also enabling interrupts. So this macro will basically make the switch to real mode. Let's create a similar one to make the switch back to protected mode. and this is also going to have 0 arguments. And what we need to do here is to basically do the reverse of what we did here. So let's disable interrupts, and then yeah, repeat steps 4 to 6 from above. Okay, so just set the protection enable flag and then do a far jump into protected mode. And then set the segments back to their original values. Okay, and I think this looks good. I'm just cross-checking with my notes here to make sure that I didn't forget anything, but I think this looks good. Yep. All right. So now let's create a function to test this. So let's do something simple first, and then we will do the disk functions, which are a bit more complicated. So let's do something simple. Let's start with, I don't know, x86 real mode D. Okay, so we are going to create a simple function to print a character in real mode, and then we're going to try to call it from C and see if that works. Okay, so first we just want to enter real mode, and yeah, we don't want to forget to enter protected mode at the end. I'm also going to set the stack frame here just to keep this code clean. Yeah, so set up stack frame. So all we have to do is just push the base pointer and then set it to ESP, and when we exit, we basically do just the restore EBP to the old value, so pop EBP. And then, yes, return. Yeah, and also to set ESP to the old EBP. Alright. And here, let's see if we can print a character. So, in order to print characters in real mode, all we have to do is set AL to SP plus 4. We are so even though we are in real mode here, but we pushed it, and actually it's not plus 4, it's plus 8, because we also have this stack frame. So we also have this BP, which is 4 bytes, and then we have another 4 bytes from the return address. So that's SP plus 4. Actually, we can just use BP this time. It's the same. Okay, so that will be the first parameter. Then we just set AH to E and int and hexadecimal, and I think this should work. Let's also declare this here. Okay, and now let's go into main, and let's write quickly a test function that will call this. Yeah, it's 86.h. Alright, and let's see if this works. I'm really curious if will this work from the first try or not. Let's see what happens. Okay. We are. Yes, it works. Look, hello from real mode. Now, let's get rid of this for loop here because we no longer need it. If I don't clear the screen, we will see this a lot more clearly. Because in real mode, it basically remembers the cursor position. And yeah, as you can see, this works very nicely. And I can call it as many times as I want. Yeah, now another thing about the BIOS interrupt is that it requires carriage return as well. Okay, and here we go. So, yay, it works. So we are basically switching to real mode, we are printing a character, and then we are switching back. And we can do this as many times as we want, and it's pretty fast. I mean, you've seen it. It is fast. I mean, for the disk operations, which you don't really have to call as often as you do these, like the put character. And I think this will work very well for the disk method. So let's go ahead and implement those. Okay, to x86.asm. Okay, now let's see what the disk methods look like previously, and we're gonna start off based on that. Okay, so let's start by implementing this get drive parameters function. This is the first one that gets called, and let's copy this one and okay, I can actually delete this because this was just a test to make sure this jumping to protected mode works. This underscore at the beginning is no longer necessary, and yes, okay, so we are starting in protected mode, so we should definitely push EBP here, not just BP. Right, so yeah, now something that I haven't done is something I wanted to mention here about these call frames is that there's an easier way of doing this, and I don't know why I did this the hard way, because there is an enter and a leave instruction. And let's see what enter and leave do, and I think these should yeah, and if I basically look at the code generated by GCC, you'll see that it actually uses enter and leave. So the syntax is that you type enter, and then this is basically the frame storage. What this means is that it's gonna basically allocate this much memory on the stack without having to like subtract from the stack manually. Now let's see. I was curious if there's any example of how to use this. Because that might be more useful. Yeah, I think that my internet connection is a bit slower because I'm streaming. Usually this works much faster. Yeah, so basically all I have to do is just call enter, then the size of the local variables, which in my case would be 0. Ah, okay, so that's the answer. Sometimes it's not used because it performs poorly. Okay, I'll just leave this one then. Yeah, okay, so then we need to save the registers. We are modifying the ES, then BX, but let's just save the entire EBX here. And SI and DI. And then we restore these. Oh, and I wonder, because ES is still a 16-bit register, even though we are in... Okay, let's see if this works. Otherwise, I'm just gonna move this lower. Yeah, and we just need to enter real mode here, and then exit real mode here. Enter protected mode. Yeah, actually, let's just leave this the way it was. And I'm just gonna leave EBX, ESI, E, and DI, and okay. And another thing that we need to change here is how we process these addresses here. Another thing that I should mention here is that so okay, I haven't declared the function, but basically the parameters, if we look here into the old get drive parameters, are okay. So the parameters are now going to be, all of them are going to be 32-bit wide, because this one's a so this one's in 8-byte value. Pushing it to the stack means that it's gonna be stretched to, it's gonna be widened to 32 bits, and since these are pointers, these are also gonna be 32-bit wide. Now, something that we need to do here is to basically convert all of these pointers to real mode pointers, because when we call this function from C, from protected mode, what we're gonna give it is an address to like a flat address, and this is something that we have to convert here. And in order to do that, let's create another macro, because why not? Macros are fun. Okay, so the way this is gonna work is we are going to let me just okay, so we are gonna get 4 parameters, and let's write a comment to segment offset address, and the first one will be the linear address, and this could also be in a register, in a 32-bit register. That's something that we will keep in mind. Then we have the target segment. So this is where we are gonna set the result. In this segment register, we are gonna set the result. Okay, I'm just gonna add out so we can okay, then we have, okay, we need to use an intermediary register, so I'm gonna put it here. Okay, so basically what we're doing here is that we're gonna take that 32-bit address, we're gonna put it in AX, and we are going to kind of split it. The lower portion we will use for the offset. I wonder if that's the right way. I think that there's a better way. So what I'm gonna do is just gonna take, okay, so I'm gonna take the bytes 1, 2, 1, 2, 3, and 4. So I'm skipping byte 0 and... is that correct? No. Okay, let me just show you. I think that's easier. Linear to seg offset 4. Okay, so first we need to put this linear address into EAX. So in order to access a parameter, we just use this percentage sign and then the parameter number. So we move... Hello. We move from this linear address, we will put it in EAX. So move... Okay. Linear address to EX. Then we need to set AX to 0. So basically we are... Yeah, so let's... Okay. So let's shift to the right by 4 bytes. So let's shift EAX to the right by 4 bits, sorry. Yeah, thank you very much, Pedro Manuel. Thank you very much for enjoying my videos, for watching them. I'm very grateful. Yeah, so what I'm doing here is basically taking the address. Okay, so let me explain what I'm trying to do here. So let's say that I have address, I don't know, 100. Okay, so I have this address. Now, in order to convert from a linear address to a segment and offset, what I'm gonna do here is I'm gonna basically divide this by 16 or remove the last digit, and this will be my segment. And then I'm gonna use the rest of it, which is just these 4 bits, and I'm gonna use these for the offset. If I do the math, so segment multiplied by 16, which means I add another 0, plus 0, which is what's left, that should give me the address that I had initially. Okay, so now I have the address in AX, so I have the segment in AX, so I can just move it to this target segment. And I don't care about the upper part of AX, I'm just gonna delete it. I'm just gonna discard it. Yeah, and this is kind of something that we will have to be careful with. Whenever we want to read something from the disk, we have to make sure that the address we give this the function, these real mode functions like get drive params or any other function, we have to make sure that the addresses we give them are in the lower side of memory, so we can access them from real mode. Okay, and finally we need to get the offset and put it in this target register. So I'm just gonna do this again. Move AX. Actually, yeah, I shouldn't use AX here. I should use percentage sign 3 because I'm using this parameter here. And then I do this step again. I already have, so I have the segment set, and now all I have to do is just get rid of the stuff that I don't need. So I'm just gonna do end, and I'm gonna put the mask 1111 or just 0xf. So dash percentage sign 3 0xf. So this means that I'm just going to discard all the other bits and I'm going to be left with a clean offset here. Okay, one macro later and we can go back to this get drive parameters function. Okay, Yeah, so in order to do this call, first we need to give it the correct disk drive, which this time is at BP plus 8. So at BP we have the call frame, and at BP plus 4 we have the return address. So at BP plus 8 is going to be the first parameter. Okay, then AH208 hexadecimal, this is good. This is good, and yeah, so we have to reset ESDI to 000 whenever we call this function. All right, and yeah, here we are preparing the return value, which is now stored in AX, but let's change that to EAX since we are and let's also put this to the stack, because I'm not sure if EAX is changed anywhere. Yeah, it is changed here in this enter protected mode function, so we need to be careful with that. And then the output parameters. Okay, so previously what I did here was I basically said I got the address, so these are basically pointers, right? And in order to write to the value pointed by this pointer, what I have to do is basically take the value of the address and store it somewhere, and then writing to the memory referenced by that address here. So that's kind of what we're doing here, what we are going to do now as well. But now we have to handle these conversions, which is a bit annoying, but yeah, we can figure that out. Okay, so let's just call linear to segment offset. The first parameter is the address that we want to set, which is this time at BP, but not plus 6, it's at BP plus 4. 8 plus 4 is 12, so it's BP plus 12. Then we want to set the segment in the AS register, and we're just going to use SI. So ESI and SI. And this looks good. Okay, now we have in okay, and now we have the address in SI and the segment in ES. So all we have to do is just copy the value from BL into this memory address here. Okay, and the same is gonna happen with all the others. Okay, so here I basically set the number of cylinders. Something that I was thinking about is that previously I had in disk.h here, when initializing I had to increment this manually, but let's take care of this in this assembly function and get a clean cylinder number. Okay, so the cylinder is in BX, so I'm just gonna increase it here as well. And now just gonna use the same linear to segment offset, and the address this time is, I add another 4, so it's 16. And then I set this in the same manner as I did previously. Okay, then we have the number of sectors. Was this one another one of these? No, I don't have to increment the number of sectors because this one's already incremented. Okay, so same as before, I take it and it's now in CX. At this point it's in CX, and all I have to do is just call this macro again, and this time I add another 4, which would be BP plus 20, and the rest is the same. And also I'm writing to segment ES here. Okay, and then the number of heads. Yeah, you know the drill. Just okay, so I'm getting it into the CX register, and then I'm just gonna call linear to segment offset, add another 4, and copy this to ES SI. Well, I copy CX. Okay, and then I'm pretty much done. But something that I modified here is I modified ESI instead of SI. I also modified the upper part of SI. So that's something I'm gonna add here and here. Okay, let's see what we have. So I'm also pushing this EAX here. I don't wanna mess this up. Okay. I can move this return statement later. So I'm first going to set all of these up, and then finally, after popping everything, I'm just gonna push the return value. And once we are in protected mode, I can just pop it back, and the rest should be history. Okay, let's see if this works. I'm just gonna run make, and okay, yeah, I no longer have this real mode. Let's delete that and replace it with this new function. Okay, and I think if there are uint8s, I think that's fine. That's perfectly fine. And for boolean, we need to include std bool. Okay, I'm gonna remove this function, and let's clean this the main file up. Okay, now here we are loaded below, so here we are loaded below 1 megabyte because we are loaded at address 500. So I can call this directly. So let's call get drive parameters for drive, the boot drive, and let's see what we get. And then we have cylinders, sectors, and head. Let me just see if I get the order right. Cylinders, sectors, and heads. Cylinders, sectors, and heads. Yep. Okay, and let's print here a message of what we got. Okay, let's run and see what we get. And we don't get anything. I wonder what the problem could be. Okay, so let's just run debug. Okay, and yeah, let's figure out whether this function. Oh, okay, I know what could be wrong, but I'm not sure. So I just need to make sure that this is 32 bits. I don't know. I mean, theoretically, it should come from here, and everything else should be 32 bits. But it's just best to specify if that's not clear. Then whenever I call this enter real mode macro, it should... okay, let's specify anyway. 16. Theoretically, when it encounters this macro, it should set it to 16 bits, but yeah, you know, it's safest to just be explicit. Okay, so I think we are getting another triple fault. Anyway, doesn't matter. Let's find what the problem is. So to do that, let's figure out where this function is. So let's go to stage2.map and find it. So it's at 5d4. Let's put a breakpoint at 5d4 and all right, and let's continue. All right. Okay, so let's go step by step and see what is happening. What I suspect is, again, the stack might be messed up, but yeah, let's see, let's check. So I should remember at the beginning of this function, base pointer was ffE4. Actually, let me just write this down so I don't forget. Whenever we exit this function, the stack should be exactly the same. If it's not, then that means we've messed up the stack. All right, let's keep this handy. And let's see. So first we set up the call frame, and then we are going into real mode. The first instruction is this jump into protected mode. Yes, we are now in 16-bit protected mode. Then we disable the protected mode bit, and then we jump to real mode. And this worked correctly. Okay, and now it should be safe to enable the interrupts. And we shouldn't get any crash. Okay, and now we are back here. Okay, so we are saving ES, BX, ESI, and DI. And then we are taking the drive and putting it in DL. And that's 00, that looks good. In AH we put the function we want to call. Okay, then ES and DI we reset them to 0, and then set the carry flag, and then call this int 13 hexadecimal. Okay. Ah, yeah, something that I messed up here, but it's just a minor thing. We're gonna fix it in just a moment. So I should do this right here after the interrupt returns, because otherwise I'm gonna lose the carry flag. Whenever we do operations like math or shifts or increment, then we lose the carry flag. So that's something that we should set here. Okay, and then right before going into protected mode, we save it. That shouldn't be much of a problem right now because we aren't checking the return value, but when we will check the return value, it should be correct. Okay, so first I am setting... Okay, so I'm basically getting the memory address and putting it in over here. I think this looks right because this the stack was FF something. Yeah, this looks good. And then we shift to the right, so we are at segment FFD. Then we... Okay, so ES should be set. Why is it 0? That's odd. Why is ES 0? It shouldn't be 0. Oh, yeah, because I'm setting AX. That is my mistake. Yeah, not AX, but %4, because this would be the 4th argument. Was that everything? No. Okay, that's not the only problem. The address was 5D4. Okay. Yeah, so I can skip over this part where I jump into real mode because we've already checked it and it looks good. Alright, and we've saved the stack and we've saved these registers, and then okay, so AX is 1, which means that this function returned true. Okay. Yeah, so now we should be at this first linear to seg offset macro. And this... Oh no, I pressed continue. No. Okay, yeah, now I should be back here at these two instructions here. Okay. Okay, so SI is FFD, that looks good, and now we are setting the extra segment, ES. And yes, this looks good. So now the address is FFD, and we add a 0, and then we add B, so FFDB, and that is right. Okay. Next we just set the value. This is something that's... this is another odd... actually, no, it looks fine. Okay, yeah, I think I can just move faster through this because I don't want to check every instruction. I just want to get to those pop instructions. Okay, so I am popping DI, ESI, BX, and ES. Then I'm pushing AX, and then I'm switching back to protected mode. So, as usual, I disable interrupts. I set the control register 0, the protected bit in carriage register 0 in control register 0, and then I jump into protected mode. And now we are in 32-bit protected mode. And we set the segments to to their correct values. Okay, EAX should now be set to 1, and this looks good. Okay, found a problem. This was easy. So I forgot that I'm using 32-bit registers here. That's basically all. Okay, so we got drive type 4, whatever that is, 80 cylinders, 18 sectors, and okay, this should be 2. So that's another thing that I have to increment. If I go here, I'm using cylinders and heads plus 1. Okay, so heads plus 1, that's another thing I'm gonna do here. Whenever I set the heads, inc.cl, and that should give me, or I can just cx. All right, and now I should get the right number. 2 heads, 18 sectors, 80 cylinders. This is the right parameters for a normal floppy disk. Okay, so now we can go ahead and implement disk.c, the initialize function, basically. We also need to add the read, reset, and actually that's all. Read and reset. Okay, reset should probably be the simplest one, so let's do that one first. All right, same as before, we have 32-bit registers because we are in 32-bit protected mode. Then we switch to real mode. And just before exiting, we exit, we enter protected mode, and these are also 32-bit. Okay, and yeah, we also have this stuff with the return value in AX, and we need to save it and then pop it after entering protected mode. All right, so this should look good. There's just one thing here. Okay, so the drive is gonna be in. This is gonna be the first argument, which is at BP plus 8. And I think the rest looks good. This is one of the simplest functions to fix. Yeah, that's pretty much it. Okay, let's also do the read. This is gonna be a bit more complicated, but not too complicated. Okay, and same as before, we have 32-bit registers. Then we jump to real mode. Then right before exiting, we go back into protected mode, and these are all 32-bit now. And what else is there? Yes, there's the return value in EAX. So I'm gonna switch to the stack before switching to protected mode, and I'm gonna pop it afterwards. Okay, now let's figure out how to fix these parameters. And yeah, the drive is also at BP plus 8, and we just add 4. Yeah, this is at 12, and here I'm getting the lower bits, and here I'm getting the upper bits of the cylinder, so that would be 13, because it's just 12 plus 1, 13. Okay. Then the next one is 12 plus 4, 16. Then another 4, this would be 20. Another 4, 24, 28, and 32. And I think that should be it. Okay, no. Yeah, so this will be a pointer to yeah, so we have another pointer here. We have a pointer to where we want to store the data, and this is something that we also have to handle using this linear to segment offset. I'm just gonna copy whatever I did previously. Okay. And the address is stored at pp plus 28, because this would be the next parameter. And we have to set ES and BX. So I would use EBX here and BX. Okay, so after calling this macro, we will have the segment in ES and the offset in BX, which looks right. And then we call the read function. And I think that's basically all. I think we're done. Yeah, and we have to save EBX instead of BX. All right, and I think we are done. Yep. Okay, now we can just move disk.c and disk.h. We can move these back into stage 2. Okay, let's see what else we need to change. Okay, so we no longer have far pointers. Something that I'm gonna do here is I'm just gonna say lower data out to make sure that we don't forget that this should be in lower memory. It shouldn't be higher than 1 megabyte. But yeah, this is just a variable name change, nothing too interesting. Have we added? No. Okay, so let's add the declarations for the read and reset as well. Okay, and this is no longer a far pointer because we no longer have far pointers, but this should also be in a lower memory, so let's add that here. All right, and I think this looks good. Yep, that's also not a far pointer. And yeah, I think that should work. I don't think we have forgotten anything. Okay. Okay, so in disk.c we have to include std bool. And these are also standard library. Okay, so okay, so I know what I did wrong. So here I no longer need to use the underscore. That's why I'm getting that compilation error. Okay, easy fix. All right, and now we should have the disk functions integrated into our stage 2. Yeah, so let's uncomment some of this code here. I'm just gonna leave the clear screen on, and then let's read a sector. So okay, let's also include disk.h. That's why I'm getting this. The end. Yes, and gdata. Okay, so this is basically this used to be a real mode address, but now we can use a normal address, like, I don't know, let's say 20,000. That should be clear. I don't think that there's anything there. So let's read LBA0. Let's just read the boot sector there, and then we will print it and make sure that we are getting the right data. So I had the function in stdio, print buffer, message buffer and count. A message, the buffer, and then count. Let's just print. Okay, let's see if this works. Okay, we are getting something. I have no idea if this is correct. Okay, it ends in 55AA, so I think this looks correct. Let's check. So let's just do a hex dump. I think I need to specify canonical was the right argument. Just check. I don't remember. Yes, it's -c, because otherwise it's gonna group them by 2, which is not something I want. Okay, and we want to print the contents of build/stage1.bin. And yes, it's EB3C90. Yeah, I think this looks good. This looks good to me. Yay! It works, which is awesome. All right. Yeah, do you guys have any more questions? Because I'm gonna end this stream here. I mean, it's been like 3 hours already, and I'd like to, and I can't stay any longer. And we're gonna do a part 2 where we just finish everything and then just write a very small kernel where we can do this stuff. So yeah, what do you think? Did you enjoy this? Was this helpful? Was this interesting? Just please let me know. If there are no further questions, then I am going to end this here. Yeah, unfortunately, I have to go. So yeah, I'm glad you learned a lot. Yeah, you're welcome. Okay, thank you very much for joining me, and yeah, we'll see you maybe in another stream soon. I don't know when. I will announce it, and we will finish this, because yeah, this is what I was planning for part 7. And then I will make the video. We'll edit the big video about part 7. Yeah, thank you very much for watching, and yeah, see you next time. Yeah, there's a Discord link somewhere. I don't know, maybe, I don't know if I put it in the description, but you should find it on the stream page, on the channel page at least. I'll make sure it's in the description if it's not. So yeah, thank you very much, and see you next time. Bye bye.